Okay, good morning, everybody. Welcome to this new episode of Control Systems. Take a seat. So, in the last few classes, we have been investigating we're investigating transfer functions. We're investigating these frequency domain relationships between inputs and outputs of systems. And we saw that we had a clear directive in mind, that is, trying to derive conclusions from on closed loop. Thanksgiving? Is it something like you're all hungry or what? No. Okay, so we have been investigating these different methods to understand how transfer function works, how to extract some information from them, and in particular, how to leverage open loop transfer functions to drive conclusions on closed loop transfer functions. So we introduced a few methods. A couple classes ago, we started talking about the root locus method, which is a graphical way to show how the poles of the closed loop system evolve, vary in the complex plane as a function of a gain in a feedback controller. Last week, Shima talked about the Nyquist plot, which is another way to represent to drive conclusions, to represent the properties of the closed loop systems by leveraging information about the plant and the controller that is on the open loop. Today, we are going to wrap up what we started a few weeks ago. Then we couldn't continue because of my absence. And we're going to talk about the Bode plots. Bode plots are another very famous and useful method to analyze a particular aspect of transfer functions, that is the frequency response. So some of you might remember that a while back we talked about this nice property of linear time invariant systems that we sort of can describe with a shortcut phrase with signs in, signs out. Now, if you send a sinusoidal signal at a given frequency in a linear time invariant system, and we wait for the steady state, we wait for the transient response to die off, then the output of the system is going to be a sinusoid at the same frequency, but with different magnitude and phase. And we saw that the magnitude and phase were scaled, and the magnitude was scaled and the phase translated by the magnitude and the phase of the transfer function evaluated at that specific frequency. So this led us to see the importance of this particular, let's say, response of the system that we called the frequency response. And one could say, well, since to some degree we can say that many signals, all inputs, could be described as a sequence of a sum of sinusoidal signals, well, if we were to know everything about the frequency response of a system, we could derive basically the outputs by leveraging the linearity of the system. So the question becomes, how do we get these, how do we describe and how do we get these parameters of the frequency response, that is, the magnitude and phase of the transfer function evaluated at a bunch of different frequencies? And, well, there is, we can represent them in different ways. The transfer function at the end of the day is nothing but, at least for CISO systems, it's nothing but one complex number. So for every S that we plug in, we get a complex variable, a complex number. And complex numbers, as we've talked about before, should immediately ring a bell that when you think complex number, you have to think magnitude, you have to think phase. Or if you want, you can think real part or imaginary part, which are fundamentally the same thing, so very strictly related. So when we looked at the Nyquist plot, we were drawing the polar plot, so the evolution of the frequency response as a, let's say, showing the real and imaginary parts where the frequency value, the omega, was a parametric variable. Well, for Bode plots, what we're going to do is we're going to explicitly show the magnitudes and the phases. So the Bode plot of a frequency response is two plots, actually. It's one plot that shows how the magnitude of this function changes in frequency, and the other plot talks about the argument or the phase. So one important thing to say about the Bode plots is that we have some fancy, let's say, conventions on the axis that, of course, make perfect sense once we go through them. On the x-axis of the Bode plots, we report the frequency on a logarithmic scale, a logarithmic scale base 10. And on the y-axis, so the Bode plots are basically two graphs, where on the x-axis we can put the omega in logarithmic scale. So it's like a log 10 of omega. And on the y-axis, on the first graph, we go and represent the magnitude of the frequency response, and on the y-axis of the second plot, its phase. Only that we do not represent the magnitude directly, but we use a weird, let's say, function of the magnitude. That is the so-called decibels. Decibels, you might have heard this unit being used in applications like, I don't know, to evaluate what is the intensity of sound. Like the law says, after some time at night, you cannot make a sound that is more than whatever decibels, right? So decibels are nothing but 20 times the logarithm base 10 of the regular value of something. So we will say this is how they're defined. The magnitude of the transfer function in decibels is this weird combination of the value of the magnitude of the frequency response in, let's say, linear terms. And one would say, okay, why in the world, right? Why are we doing this? Well, that's usually because, that's because if you recall, a transfer function in the most general case is representable as a ratio of polynomials. And we can break down the numerator and the denominator so to be a product of a bunch of terms. So here we're just showing these terms in this way. And when we take the magnitude of a ratio of polynomials, factored in some ways, well, we know that the magnitude is the product of the magnitudes at the numerator divided by the products of the magnitudes at the denominator. But if we use logarithms to express this magnitude, then, well, logarithms have their own properties, which are very nice. That, in particular, the fact that if you have the logarithm of a product of something, well, that's equivalent to the sum of the logarithms, right? You have the logarithm of the ratio of something, well, that's equivalent to the difference of logarithms. So just by using this, this weird unit on the y-axis of the magnitude of the Bode plots, the decibels, we can express we can represent the frequency response of the system by analyzing one of these factors at the time, at the numerator, at the denominator, and just add them up, add or subtract them. And this is nice because we can do the same thing for the phase. Phases, if you take the phase of a complex number that is expressed like a product or a ratio of specific terms, we saw this many times already. We can express the phase as the sum of the phases of the products at the numerator minus the sum of the phases as the product at the denominator. So by putting these things together, we will see that Bode plots allow us to do something very nice, which is focus only on one of the factors at the time. And once we figure out what the magnitudes and phases are of each of these possible factors that we can find at numerator or denominator of frequency responses, then the most complex cases get just, how do you say it? You can just reconduce them to a sum of the simpler ones. And we'll see some examples of this today. Another nice property is that, well, always by leveraging logarithms, we can let's say, for example, the magnitude of a term that is at the numerator or at the denominator, but just putting a minus in front of it. Because the logarithm of 1 over something is equal to minus the logarithm of something, right? So, okay, there are different ways to go about mapping this frequency response. One thing that is important to know, although it's not going to be the focus of what we're going to be doing in this class and the rest of the course, is the, let's say, going in the direction from when one doesn't know anything about a plant, a system that you want to control, but you're in the process of trying to extract a model of it. Say that for some reason physics doesn't help you and you're not really sure how to derive this model of the system through, let's say, first principles. Well, one can just do, for example, what is called a frequency sweep. That is, send to the system an input, which is a sinusoid at a specific frequency, let's say at 0.1 radians per second, and wait for the system to get to steady state. So wait until the output doesn't have a transient anymore, and go and measure what is the ratio of the magnitudes of the outputs to the inputs, and that tells us what is the magnitude of the transfer function at that specific point in frequency. And by just measuring what the difference of the phases is, one gets the information on the phase of the transfer function at that specific point in frequency. And if one just has a lot of patience and does this a frequency at the time, one can literally map out what is the frequency response of a system. So it's somewhat a way to discover what is the mapping between inputs and outputs for the linear system. Of course, this assumes that you're describing the system as a linear time invariant system. And it's powerful because it provides some information. Once we have these data points, one can fit them, for example, and now you've got a model of your system without having to write the physical equations. And so this is something that is useful in practice. Many times, even if you have a model of the system, you, in practical application, might want to double check if your model actually makes sense with the real hardware you have in front of you. So you would just explore the response of the system at a set of frequencies and match if the model makes sense, and that gives us some validation on the model. The other direction instead, which is, let's say, the one that we're going to be investigating more thoroughly, is not from data to transfer function, but to frequency response, but from frequency response to Bode plots, okay? So basically, we suppose that somebody is giving us a model of the system, represented in a form of a transfer function, for example, and then we extract the frequency response by substituting in place of S in the transfer function, the value j omega. And by breaking down any transfer function as complex as one wants, reconducing it to its factors, we'll see that basically all there is 4 kinds of terms that we will have to deal with. And thanks to the use of decibels and the properties of complex numbers, as we said a few slides ago, well, then even the most complex transfer function gets reconduced to the sum of its terms. So what are the terms? Well, if you break down a polynomial, you can break it down to products of 4 fundamental factors. A constant factor, just a number. Let's say an integrator or a differentiator, or a monomial factor, which is like an S or a j omega. Let's say a pole or a zero, a stable pole or a zero, which we can represent as 1 plus tau s, and we call tau the time constant and 1 over tau the breakout frequency. And note how we kind of use terminology here as stable pole or zero because, well, it really depends where you find this term. Now, it could be at the numerator or the denominator, but still the properties of it are the same. Or in the most complex case, we can find, let's say, a complex conjugate pair of poles or zeros in the form of a trinomial term like this. So what is important to say from a practical perspective, let's say from an exam point of view, when from a student perspective, you want to make sure that you look at these terms and keep in mind that everything we're going to do for the next 45 minutes or so is based on the assumption that those terms are written in that way, okay? So don't get fooled by somebody that might or might not in the exam give you a transfer function that you have to turn out in a frequency response that maybe is in the form, I don't know, omega n plus 2 zeta j omega plus j omega squared, something like that, okay? Be careful that you want to make sure that all terms you're analyzed are expressed in the form that they're written here, okay? So that they have a +1 term. So what is the procedure to get to Bode plots? Well, step one is get a frequency response from a transfer function, but just plugging j omega instead of s. Step two, break it down to the factors. Zeros, poles, and you either get constant terms, monomials, binomials, or trinomials, numerator and denominator. Then analyze one term at a time, draw them all together, sum them up at the end. Doesn't matter how complex the frequency response you're dealing with, this method works pretty much always. So the key part now is figuring out what are the magnitudes and phases of each one of these blocks, of these terms. So, well, let's start easy, right? What is the magnitudes and phases of a constant, right? It's one of the four terms, so let's look at it. So here we're going to use a standard method, basically. So, well, suppose that we have our transfer function that is given to us as g of s equals some constant. The first step we said is plug in every time you see s, j omega. There's no s's, there's nothing to plug in. The Bode plots are these two plots here. As you see, we've got a magnitude on the y-axis of the first plot and expressed in decibels. So this is 20 times the logarithm in base 10 of the linear version, let's say, of the magnitude of the frequency response, while the other plot shows how the phase of the frequency response varies as a function of frequency. And the frequencies, which are omegas here, we show them in a logarithmic scale. Note how the logarithmic scale has these spacings, let's call them, that are called decades, okay? So when we refer to a decade, all we're saying is the, let's say, spacing between two of these points on the logarithmic scales, which are basically different orders of magnitude of the frequency, no? So 10 to the 0 would mean 1 hertz, or radians per second here if we're representing it as omegas. 10 to the 1 would represent 10 radians per second. 10 square would be 100, right? So here it's 0.1, 0.001. Okay, so what is the magnitude of a constant expressed in dBs? Well, just so that we keep it in mind for the rest of the class, don't forget that if we have any complex number, let's represent it like this. This is complex number z, and this is the real axis, and this is the imaginary axis. Well, if z is equal to a plus bj, where a is the real part, b is the imaginary part, then the magnitude of z is nothing but the root of the squares of the imaginaries and the real part, and the phase is nothing but the inverse tangent of the imaginary part over the real one. Everybody agrees with this, right? This is like in our bloodstream now. So, well, basically all we have to do is this for the next 4 terms, being a little bit careful to details and remembering to express decibels instead of magnitudes in their linear form. So, okay, let's look at the magnitude of the constant. Well, we'll express it directly in dBs. There is only a real part, so this is directly 20 times log 10, the magnitude of k. So, for example, suppose that k is equal to 1, then 20 So suppose k is equal to 10, actually, then 20 times log 10 of 10 is equal to 20 dBs, okay? So the magnitude of k would be 20 for all frequencies because it doesn't depend on frequency. What about the phase? Well, the phase is equal, we said, to the tangent inverse of the imaginary part over the real part. But k doesn't have an imaginary part, right? Because we're assuming that k is the feedback gain, or for example, it's a feedback gain, and it's a real number. Well, the real part is k. So this is 0 over k is a weird way of saying 0. So the arctangent of 0 is 0 if the constant is a positive one, or it's minus pi if the constant is a negative one, right? So the phase of a negative number is minus 180. Please note that the phases can be expressed in both phases or radians. Doesn't really matter. You'll kind of find them in both ways. Just make sure you're consistent. So if we suppose that k is a positive number, then the phase of a constant would be 0 throughout the whole frequencies. If instead the k is a negative number, you would have minus 180 throughout all frequencies. Does this make any sense? Seems trivial, right? It kind of is. We have a constant. All we're doing is we're finding the decibels and the phase, magnitudes and phases. And we're expressing them as a function of omega. Okay, let's scale it up a little bit. Now, suppose that we're looking at an integrator term, okay? So it's a monomial, it's just an S. Well, let's pretend it's a 1 over S, okay? So what's the first step? Well, let's extract the frequency response. So let's plug in j omega instead of S. So g of j omega is 1 over j omega, which can be rewritten as minus j 1 over omega by just multiplying numerator and denominator by j, right? Okay, so what does this tell us? This tells us that this term has a a real part that is equal to what? A real part that is equal to 0, right? Because there is no real part. The only term that we find is multiplied by the imaginary particle. And on the other side, the imaginary part is minus 1 over omega. Okay, so what is the magnitude of this monomial term expressed in dBs? Well, it's 20 times the logarithm base 10 of the magnitude of the term. So what is the magnitude of the term in linear? Well, it's the square of the real part, which is 0 squared, plus the imaginary part squared, right? So this is equal to 1 over omega. So the logarithm in base 10 of 1 over omega is minus the logarithm of omega because you can just, because logarithm of 1 over a is equal to logarithm of a inverse, which is equal to minus logarithm of a. And so what does this tell us? This tells us that when you find an integrator term, a 1 over s, well, this is basically in the Bode plots, a slope, a line that has a slope of minus 20 dBs per decade. What about the phase? Well, same method as before. So these Bode plots are really kind of simple because we can apply this same method over all the terms and then we just sum things up. But once we need to see how they work. So, well, what about the phase? Tangent inverse of imaginary part over real one. What's the imaginary part? The imaginary part is minus 1 over omega. The real part is 0. So this is, since the frequencies are always positive, this is a term that tends to infinity. So the tangent of infinity for a negative on the minus side is minus pi half. So an integrator term will always have a phase of minus 90 degrees, like this. Does it make sense? So what's the difference from a constant? Well, a constant is a constant, doesn't vary in frequency. Well, an integrator term, if you have an S, Well, if you have at the denominator, you will find you have this magnitude that varies in frequencies as a line that has a slope of 20 dBs for every decade of the frequencies. Now, keep in mind that we're looking this as a denominator term, no? So what instead if you found the S at the numerator? Well, the magnitudes would be the same thing, but just flipped over with respect to this axis here. So just keep in mind, incidentally here, this is a very common mistake that is done. When you see 0, this is not 0 as in 0. These are 0 dBs, okay? So remember the fundamental relationship, the definition of decibels. If you have something in dBs, this is 20 times the logarithm and base 10 of that something in, let's say, normal linear terms. You can flip this over and you'll see that the linear version is what? It's 10 to G in dBs over 20, correct? So if you ask yourself, what is 0 dBs? Well, if you plug in 0 here, you get 10 to the 0, which is 1. So this really means 1 in linear terms. Don't get confused by the 0 dBs being 0 in linear terms. No, 0 dBs means 1. Okay, now let's get a little bit more interesting. Let's see if I can. So let's suppose now we're looking at a binomial term, okay? So it's 1 pi plus tau s. Let's suppose we have it at the numerator, okay? And we will study the properties at the numerator, and then it's going to be easy to extract properties at the denominator. Same approach as before. What is the magnitude? What is the phase? Well, what's the real part of this term is what? Well, first thing, you plug in j omega. So you get 1 plus tau j omega. So the real part is 1. And the imaginary part is what? The imaginary part is omega tau, right? So what's the magnitude of this term as a function of frequency? That's 20, expressed in dBs, that's 20 times logarithm 10 of the magnitude of the term expressed in linear, which is the root of the sum of the squares. So 1 square is 1, and omega tau square is omega squared tau square. If we look at the phase, well, we have the tangent inverse of the imaginary part over the real part, which is omega tau divided by 1. So that's the expression. Now, these are not really nice terms. It's difficult to easily write them down. So since the whole motivation of these different geometrical approaches that we've been seeing, the root locus, Bode plots, Nyquist plots, are all kind of to provide an insight that is simple, that is quick, that is powerful, but at the same time doesn't require a lot of computation. What we do to draw these terms is to simplify them to something that are called asymptotic approximations. So basically what we're going to say is, we don't really care exactly how this plots out in the frequencies, but we're going to do some approximations so that it becomes very, very simple to really sketch these terms quickly. And still, the insight that we gain is powerful. Then once the qualitative insight comes in, we can maybe plot everything at a computer and get the exact response. So how do these approximations work? Well, suppose that we are going to say, okay, we analyze the asymptotic behaviors. Asymptotic as omega goes to 0 and as omega grows to infinity, becomes very large, but very large in respect to what? So if omega is very smaller than 1 over tau, or the absolute value of tau, what happens? Let's look at this term here, 20 times logarithm in base 10 of the root of 1 plus omega squared tau squared. Now, if omega is much smaller than 1 over tau, this means that omega tau is much smaller than 1, correct? Yes, no, maybe. We're going to do a few of these things, so you have to get useful now with you have to get used to how we're going to start approximating and neglecting things. So we just made an assumption that omega is very small. Very small, what does it mean, very small? It means very small with respect to something. What in particular? Well, in this case, with respect to 1 over tau. Why do we choose 1 over tau? Well, because we want to approximate this term here. So what we really, the direction in which we're going is we're going to make some assumptions such that we can say something of the term omega squared tau squared with respect to the term 1. So if we say omega is much smaller than 1 over tau, this means that omega tau it's much smaller than 1. If omega tau it's much smaller than 1, then the square of it is going to be much, much, much smaller than 1. So it means that we can neglect this term here with respect to 1. So in this approximation, today is the remote. Okay. In this approximation, the magnitude in decibels of the frequency response is 20 logarithm of the root of 1, which is 0 dBs. Don't forget that logarithms go like this. So the logarithm of 1 is 0, right? So, okay, this is nice. How shall we represent it? I would like to figure out how to show both pages. You know what I mean? Okay, give me a second here. Okay, might not be the best way, but can you see? Yes, right? Fair enough. Okay, so I'm going to use this plot down here to make the point. Here we're showing a particular case of what we're saying. It's like plug in some numbers, get 1 over s plus 1 and show it, right? But here I want to plot out the general case. So we have omega. Here we're going to show the magnitude. I'll just put dots here to say I don't want to rewrite g of j omega every time, okay? So here's the magnitude of the frequency response in decibels. And here we're going to show the phase. Okay, so you remember these are the decades. And the typical thing you do is you just start from the center and you say, okay, what do you say? Now, what do we put in the x-axis? Well, of course, it has to span the whole frequency, let's say, from zeros to infinity, so to speak. But since we don't have infinite decades, you kind of want to focus somewhere. Well, here we made an assumption. We said that the magnitude of this term is equal to 0 dBs when omega is much smaller than 1 over tau. Well, fantastic. So suppose that we have here 1 over the magnitude of tau, then what does much smaller mean? I mean, we're doing an approximation here, so we have to agree to something, no? Much smaller, what is much smaller? Much smaller, let's make an order of magnitude. That's like kind of the standard for much smaller. So an order of if this is 1 over tau, then this decade here is going to be 0.1 over tau. This decade here is going to be 0.01 over tau. This one here is going to be 10 over tau, and so on, right? So see how Bode plots are typically shown one on top of each other, right? Because if we align the frequencies, remember that at the end, what we're going to do is sum up the contribution of each term. So if we plot them all on the same graph and we align the frequencies, then it becomes really easy to just sum them up. So it will become clear in a while, but just note that we always plot the Bode plots one on top of each other. So, okay, suppose this is 1 over tau. We said that the magnitude is 0 dBs when the frequency is much smaller than 1 over tau. So much smaller, we say 1 order of magnitude smaller. So it means that suppose that this is 0 dBs, we're going to have this value here of the magnitude up to a frequency that is 0.1 times divided by the breakout frequency, so divided by tau. And what about the behavior when we have very high frequencies? So what does very high frequency mean? Well, very high is always with respect to tau. So in this case, we have okay, what if omega is much bigger than 1 over tau? Well, this is a way of saying that omega tau is much, much bigger than 1. Well, if omega tau is much, much bigger than 1, then when we look at the magnitude, if it's much, much bigger than 1, this term here, it means we can neglect 1 with respect to that one, because it's much smaller. So we can approximate the magnitude at very high frequencies as 20 times the logarithm of omega tau, which can be broken down as the sum of these two terms. Now, if we look at those two terms, what does it tell us? Well, it tells us that the magnitude in dBs of a binomial term is a slope at high frequencies that has, it's a line at high frequencies that has a slope of 20 dBs per decade and crosses the x-axis, if you want, when omega is equal to 1 over tau. So basically what we're saying is that, say that this is 0, this is 10 dBs, this is 20 dBs, this is 30 dBs, and so on. This, we said, is the frequency 1 over tau at very high frequencies. So we have to kind of agree to this. What does very high frequency mean? Well, if we said that very small is 1 order of magnitude smaller, we could say that very big is an order of magnitude bigger. So if this is the frequency 1 over tau, the next decade is the frequency 10 over tau, so 1 order of magnitude bigger. And so we're saying that basically this is where omega tau is much bigger than 1. And this is where omega tau is much smaller than 1. So in this, let's say, high frequency part, we have a slope that is, we have a line that is basically this. So it passes through the point, so through it intersects the x-axis at the breakout frequency. Is kind of why where the name comes from. And it's, sorry, I think I draw it badly because it has a slope of 20 dBs per decade. So what does that mean? Well, this is a decade. We said that these are 10 dBs, these are 20 dBs. So boom, here it is. Now, of course, this approximation is only valid at high frequencies, right? Because that's how we derived it. So what happens in the middle? Well, in the middle, we will do we will just approximate and say, well, it's 0 up to here, and then it grows like this. So it's easy to draw. This is not really what the value of the magnitude of the transfer function is, but it's very close. It's close enough that it's an approximation that we can do in order to drive conclusions from transfer functions. If you want to really know what the real values would be, well, what is typically said, not that it's particularly important, but what is typically, the real thing is that it would do like this. So basically, it would asymptotically tend to our approximations at the low and high frequencies, and sorry about this. The maximum error happens here at the breakout frequency, and it is an error of 3 dBs. And this can be derived by just plugging in the right values, but it's not important. You don't need to know this. The only thing I want to tell you through this fact is just that we're doing asymptotic approximations to speed up the process of writing things and deriving some information, insight on frequency responses, but we're not showing the exact real thing, okay? And if you really want the exact real thing, well, go plot it at a computer or have a lot of patience and do it by hand by actually not doing the approximations. The biggest error you have is of 3 dBs there. Okay, then let's look at the phase. Let me switch back to blue. So how does the phase of this term works? Well, what's the phase of 1 plus tau s? Well, the phase, we said, is the tangent inverse of what? Of the imaginary part over the real part. So what's the imaginary part? The imaginary part here is omega tau. And what's the real part? The real part is 1, right? So what happens when omega tau is much smaller than 1, when it's very small? Well, when it's very small, it means this term here is very smaller with respect to the denominator. It goes to 0. So the tangent inverse of 0 is 0. What if omega tau is very big? Well, if omega tau is very big with respect to 1, then this is, the tangent inverse is the tangent inverse of a very big number, of infinity. So, as if you remember the tangent plot, if you have a tangent that is very big and it's positive, you will have a pi half 90 degrees phase. If instead the tau, consider omega is always a positive number, so if tau instead for some reason is negative, then you're always going to infinity but to minus infinity, so the arctangent of minus infinity is minus 90 degrees. Okay, so how does the Bode plot, the phase of a monomial term look like? Well, let's go back here. We suppose that, I don't know, this is 0 degrees, okay? Suppose we're expressing all of this in degrees now. So very big, very small, it's always with respect to the breakout frequency, right? So I'll pretend here, I'll continue bringing down these two regions, although we'll not show them again in the future. So very small with respect to the breakout frequencies, what did we say? We said that the phase was equal to 0, okay? So 0, 0, 0, 0 up to here. Then what happens? At very high frequency, a decade bigger than the breakout frequency, we have 90 degrees if tau is bigger than 0, minus 90 degrees if, so let's say that this is 90 degrees and this is minus 90 degrees. Then it's either here or here. This is the case of tau being bigger than 0. This is the case of tau being smaller than 0. And what happens in the middle? Well, we just approximate by doing a line. So really, the real thing would be slightly different. But again, same argument as before. The real thing might be something like this. But it's a tolerable approximation. So, make sense? Good, right? Okay. So remember, this is when we have this term at the numerator. If we have it at the denominator, well, then we're going to flip magnitudes and phases, right? Okay, let's get to, we only have a few minutes, but still, let's start looking at the trinomial term that is arguably the only complicated thing there is to say about Bode plots. What's the procedure? Exactly the one we've been following up to now. So you're given a pair of complex conjugate poles or zeros that can be expressed as this term here. Now, please make sure that you put it in the Bode form, which means it's +1 at the end. And first step, plug in j omega. Here we go. Find what are the real parts and what are the imaginary parts. Well, the real part of this is what? The real part of this is 1 minus omega over omega n square, correct? Because if you just take the square, j square is equal to -1, and you've got the real part that is the first and the third term. And the imaginary part instead is what? The imaginary part is twice zeta omega over omega n. And we call omega n the natural frequency, and we call zeta the damping term in this case. And we assume that the damping term can be between -1 and 1. I'll just write this here. I forgot to write it down. Okay, so same game as before. Magnitudes and phases. How do we go about finding them? Applying the definition. The magnitude in dBs is 20 times the logarithm 10 of the square of the sum of the root of the sum of the squares. Sum of the squares of the real part and the imaginary part. Okay? And this, if you check, is nothing but the square of the real part and the square of the imaginary part. What about the phase? The phase is the ratio, the tangent inverse of the ratio of the imaginary part over the real part. Same exact thing as we've been doing up to now. The question now becomes, okay, how do the approximations work? And I guess we'll figure this out after the break. Okay, here we are. You got 2 extra minutes. Don't get used to it. Okie dokie, so where were we? We are looking now at the Bode plots of complex conjugate poles are zeros. So we all agree that we can just apply the definitions of magnitudes and phases, and we get to these expressions here. Now, how do we do the asymptotic approximations in this case? Again, the objective is to simplify these terms, right? So as you see, we have comparisons of terms of ones and ratios of frequencies over the natural frequency because of the particular form that we chose in expressing this. So we're going to say, okay, what happens if omega is much smaller than omega n? Well, if omega is much smaller than omega n, this means that omega over omega n is much, much smaller than 1. So if this is smaller than 1, well, then this term is negligible with respect to 1. This becomes 1 squared, which is 1. And then this term here is negligible with respect to 1 again, because the zeta is bounded between 0 and 1. So this means that in this approximation, the linear magnitude is the root of 1, which is 0 dB. 20 logarithm base 10 of 1 is 0. What about the phase instead? Well, let's look at the phase approximation. If we say that omega over omega n is much, much smaller than 1, then the square is really much, much smaller, even smaller than 1. And this goes to 0 with respect to 1. So we have basically the tangent inverse of 0. And what is it? Well, it depends on zeta, but it depends on zeta. It could be either 0 or minus 180, depending on how what the sign of zeta is. What about the other direction? So the high frequency approximation. Well, so let's draw this. Let's suppose that we have omega n here. Okay. So this means that this is going to be 0.1 omega n, and this is going to be 0.01 omega n, and this is 1 decade above, and this is 2 decades above. Again, we're showing here the phase. Let's express them in degrees, and here we're showing the magnitude, which we express in dBs. Okay, so what have we been saying? That suppose that this is 0 dBs, and this is 10, this is 20, and so on. Then what we're saying is that the approximation, anything under here falls under the approximation of this omega much smaller than omega n, and here omega much bigger than omega n. So what we said is that the magnitudes at low frequencies with respect to the natural frequencies have 0 dBs. And the phases have, let's say, zeta is positive, 0 as well. These are degrees. Now, what happens for the high frequencies? Well, let's look at this a little bit more carefully. So if omega is much bigger than omega n, this means that omega over omega n is much, much bigger than 1. So let's go back to our definitions here of magnitudes and phases. So if omega over omega n is much, much bigger than 1, it means that 1 is negligible with respect to omega over omega n, right? So here we get, basically, for the magnitude, 20 log 10 of what? Of omega over omega n at the 4th power, plus something of the order of omega over omega n at the square. So if omega over omega n is a very big number, then this dominates. This term is negligible with respect to the 4th power. And therefore, we can approximate at high frequencies the behavior of the magnitude expressed in dBs as the root of the 4th power means the square, 20 times logarithm base 10 of this, which can be expressed as 40 times logarithm in base 10 of omega minus 40 times the logarithm in base 10 of omega n. And what is this? This is a line, again, that intersects the x-axis at omega equal omega n, but has 40 dBs per decade, because the coefficient there is 40, right? So what we're saying is that if we go at high frequencies, so this region here, well, we have a line that crosses the I'm looking at the wrong graph. Crosses the x-axis here and goes every decade, 1, 2, 3, 40 dBs per decade. So it's something like this. Okay. So what happens in the region where our approximations don't hold really well? Well. So here it really depends on the damping coefficient, on zeta. So let's look at, for example, what happens if zeta is equal to 1. So I will just write it here. So suppose that, so let me see. We have, our term is 1 plus 2 zeta omega over omega n j plus j omega over omega n square. If zeta is equal to 1, we get 1 plus 2 omega over omega n plus blah, blah, blah. Right? If you look at it, this is exactly a 1 plus tau s square. So when zeta is equal to 1, this is nothing but the square of a binomial term. So the binomial term was expressed like this. So if you have a square, it means that all you do is, it means the product of two of the same. It's like sort of trivial. This means that their logarithms sum up. So in fact, instead of getting something that goes up with 20 dB per decade, you get something that goes up with 40 dBs per decade. Right? So when zeta is equal to 1, you have this behavior here. Okay. Now, what if zeta is equal to 0? Let's look at the extremes, right? So if zeta is equal to 0, where can we look at it? If zeta, let's look at the magnitude, okay? So if zeta is equal to 0, this term goes to 0, right? And what happens in this point here? Well, in this point here, omega is equal to omega n. So omega over omega n is equal to what? It's equal to 1. 1 minus 1 is 0. What's the logarithm of 0? Logarithm of 0, high school? Logarithm of 0. What's the logarithm of 0? Minus infinity. So we've got minus infinity down here. So when zeta is equal to 0, you've got an asymptote. What does it mean? It means that, on the left side, so in case of zeta equal to 0, we can show that the behavior in the region in which the approximations don't hold can be approximated like this. This is zeta equal to 0, okay? Where at the exact value of the natural frequency, there is an infinite response. This is resonance, no? And, okay, so if 0 is there and 1 is the other case, we've got the two boundaries for any value of zeta in between. We could do the exact calculations, but we really don't care, so we can just approximate it like this. So this is, as zeta grows, it goes from 0 to 1, and goes from the asymptotics, from having an asymptote to being the square of a binomial term. Does it make sense? Okay, so this is like kind of the only thing you can be tricked upon when you do Bode plots. So what about instead the phases? So same deal as before. The phases, if you just take the phase equation and do the same reasoning that we have been doing up to now, we will say that for high values for low values, we are at 0. For high values, we are at 180. So this is 90. Let's say this is 180. And this is minus 180 degrees. So we can go to either here or here, like this or like this, depending on the sign of zeta. Always remember that these combinations, we have to derive them by assuming, for example, in this case, that we're looking at a complex conjugate pair of zeros, right, in this case, because we've been analyzing the form directly like this. If in an exercise you get that form at a denominator, then really the contribution of that term is 1 over what we just said. And when you have 1 over something and you look at the magnitudes and the phases, if you're using decibels for the magnitudes, which is the case of Bode plots, all you have to do is put a minus in front of it. So these graphs that we've seen here are valid if this term is at the numerator. If you find this term at the denominator, you're gonna flip them. It's gonna be the exact symmetric solution with respect to it's gonna be like this, with the axis up here, blah, blah, blah. Okay, it's like exactly the flipped solution. Okay, so we understood now what is the contribute in terms of magnitude and phase of each one of these terms. How do we put things together and actually make something useful out of it? Well, let's look at an example. So let's look at an example, and let me go back to a single page. So suppose with a classical exercise, sketch the Bode plots of this transfer function. So first step, you put it in Bode form, which means make sure each one of these terms is written in the same way that we have shown them. A very classical thing is this like s plus 2. Well, s plus 2 is not in the form 1 plus tau s. Maybe this is not right thing to say, but you see the forms are different. So this would, before starting to apply the rules that we just saw, you would express it like this. So a classical term s plus 2, really when you apply the Bode plots rules, it breaks down in two different terms. There's a constant 2 and there's the binomial term s half plus 1, where in this case tau would be what? Would be 1/2, right? So the breakout frequency would be 2. Okay, so that's the only real parameter you need to then draw the Bode plots. First thing, so put everything in Bode plot form. Plug j omega in place of s, so you can calculate if you want to do the math, you calculate the magnitudes and the phases. If you just remember by heart the rules that we've said, you don't even need to plug in j omega. Then you draw each factor, and then you sum everything up. And the nice thing about semi-logarithmic paper is that it aligns everything, so you just need to find the ranges of frequencies and add all you find. Let's look at a term at a time. So suppose this is the function we need to study. Colors help. We start from the top term here, which is s half plus 1. What does it mean? Well, it's a binomial term. It's a 1 plus tau s term. It's at the numerator. And the breakout frequency is what? As we just said, is tau, if tau is equal to 1/2, the breakout frequency is 1 over tau, which is equal to 2. So look at the frequency axis, okay? We have this very characteristic, you read it as 10 to the 0, 10 to the 1, 10 to the 2, because they're powers of 10, right? So this means 1, 10, 100, 1,000, and so on, right? 0.1, 0.01. So these intermediate dots here, if this is 1 and this is 10, this is going to be 2, this is going to be 3, this is going to be 4, and so on. It's going to be 0.2, 0.3, and so on, okay? So what is the contribute of this first term to the magnitude? Well, if you recall, you can go back through the slides, we're going to have a breakout frequency at 2 hertz, which is 1 over tau, and it's going to grow with 20 dBs per decade after that. Okay, so this first term is this one here. What about the phase of this first term? Well, this first term is at the numerator. Tau is a positive number, so it's going to give a contribute of 0 degrees at low frequencies and 90 degrees at high frequencies. And in the middle, we just connect with an asymptote with a line. You get this here. This is s half plus 1. Okay, now let's go to the next term, s over 10 plus 1. It's exactly the same thing, but now the breakout frequency is 10 instead of 1. So where do we go and find that one? Well, now we're looking at the decades, right? So if this was 10 to the 0, you see they're aligned. So basically 10 to the 0 here is the same frequency value in the upper graph. The next decade is 10 to the 1, which is 1. So this, sorry, 10 to the 1, which is 10. So here, this is the breakout frequency of this term here. Same behavior, 0, 0, 0 up to the breakout frequency, and then it grows with 20 dBs per decade. Okay? Now, let's look for a second at this term here, which is exactly the same term, but this time is at the denominator. Okay, so by the way, the phase contribution of S over 10 plus 1 is the same as before. It's 0 up to a decade before the breakout frequency. It's 90 degrees a decade after the breakout frequency. In the middle, you just connect to the line. So you see, here is the 1 decade above the breakout frequency. The breakout frequency for this term is, we said, 10. So 1 decade above is 100. So from here on, you've got 90 degrees. From 1 decade before, you've got 0. In the middle, you just connect with a line. Okay? Now, don't worry about the rest. Here, the cool thing about Bode plots is we look at the term at a time. Okay? And we just apply what we learned before. Once we wrote down all the terms, we'll worry about summing them up. Okay, now let's look at the other easy one, S over 5 plus 1. It's exact same things, but this time it's at the denominator, okay? So what does it mean at the denominator? It means the magnitude is minus the magnitude, and the phase is flipped. So what's the tau here? If tau is 1/5, yes it is, so the breakout frequency of this term here is 5. So if this is 1, 1, 2, 3, 4, and 5, this is frequency 5. Let's see, 1, 2, 3, 4, and 5 here. So we should have at this point, you see, this term here has the breakout frequency here. It means 0, 0, 0 up to there. And then it decreases, not increases, with always a slope of minus 20 dB per decade. It's the same thing as before, but we just did the symmetric. And same goes with the frequency, with the phase contribution. So here we are at 5, 1 decade above, it's 50. And it's minus 90 degrees this time. 1 decade below, it's 0.5, and it's 0 in the middle, connect with a line. So it's the same thing as we did at the numerator, only at this time it was at the denominator. So if you don't trust these properties, you could just repeat the exact same process we did before, by instead of considering 1 plus tau s, write it down as 1 over 1 plus tau s. The first thing you do is you just see that it's the inverse. So if you do the logarithm of an inverse term, the minus becomes a minus that multiplies the logarithm. This is kind of the reason why we choose dBs on the y-axis. Okay, now let's look at the other term. Let's look at the trinomial term, this s squared plus s plus 1. Well. So remember that we like to see it in the form s, so we defined it in what we studied in the form s squared over omega n squared plus 2 zeta s over omega n plus 1. Okay, so we kind of have to recognize who's who here. So who's omega n, who's zeta? Well, by inspection, we can say that omega n is equal to 1 and zeta is equal to 1 in that term. Correct? Do you agree? You're correct. So, well, at this point, what we have to do is go and plug in this term. So, it's the blue one. And what do we have? We have the breakout frequency here is this one. It's omega n equal to 1, which is 10 to the 0. So what did we say about these? At high frequency, so it means at 10 to the 1, it's a slope of 40 dBs per decade. So it's a line that passes through the breakout frequency, but has a slope of, in 1 decade, it goes down 40, so it would be this. And up to 1 decade before is 0. And then in the middle, we'll just have to approximate it with something because zeta is equal to 1/2. So it's going to be something like this. While the phase, it's going to be something that for 1 decade before, it goes to 0. 1 decade above, it goes to minus 180 because it's a term at the denominator and zeta is bigger than 0. And in the middle, you just connect with a line. Okay, now what do we do with all these terms? Oh, it looks like a big mess. It's a big mess up to a certain point because now we can, by the way, no, I forgot one term which is very important here. Heroes fall for these things. We didn't analyze all the terms. We forgot the constant, the 2. The 2 is a term, it's there, okay? So what is 2? 2 is a constant term. It's positive, it's bigger than 0. So it means that it gives a contribution that is in magnitude that is constant over all frequencies. This is 2 dBs, whatever that is. And in phase, it gives a 0-degree contribution over all frequencies because it's a positive number. Don't forget the constants, they play a role. Okay, so now what we do, we just go and see, well, look, from 0 frequency, it's not 0, 0, 0, epsilon, omega equals epsilon up to here, it's the first time, no, here's the first time something happens. We just sum up all the terms of the magnitude, and we sum up all the terms of the phase. So you get, in fact, a magnitude that goes like this up to here, and then 0 up to here. And so on and so forth for all of these regions until new breakout points happen. If you sum the terms one by one, you get this black approximation. So we just broken down a complex transfer function into these 4 kind of terms. You draw each one of them, plug them in, and you sum them up. What the real behavior would be if you were to plug this in a computer is given by the light blue line there, which is kind of okay. It's close enough, okay? Perfect, fantastic. Now, we learned how to do Bode plots, but why are they important, right? We will get to that. Are there any questions on this? Yes? I think the tones should be different, but they are really not. I think that, so this is this red here, this is this red here. It's a mistake. The dark blue line is missing. I drew it by hand. There is for the phase here, but it's missing on top. I'll fix it. Thank you. Okay, so, it turns out that Bode plots are useful for drawing Nyquist plots. And let's look at a few examples so we can actually practice with both Bode plots and Nyquist plots. Okay, so suppose that we are given this transfer function. And what are we going to do about it? We want to draw the Bode diagrams and the Nyquist plots. And we want to ask ourselves, for example, for what values of k, all of this is the open loop transfer function of a system, for example. Suppose we are studying a problem like this. We choose k to be a controller. The L of S actually is not L of S. This is a G of S. That is S plus 1 over 2S minus 1, 3S minus 1. And this is the output. And suppose we're doing the feedback here, and we're asking us for what values of k does this, is this stable or not, right? So let's start by drawing the Bode plots. So we need some patience here. So I'll actually sit down. Okay, so let's start from drawing the diagrams correctly. So this is the omega axis. This is the magnitude in dBs. This is the phase in, let's say, degrees. Let's call I would go with this frequency being 10 to the 0, this being 10 to the 1, this being 10 to the square, 10 to the minus 1, 10 to the minus 2. Okay, and of course, these are the equivalent from below. I won't rewrite them just not to make a mess. Okay, so what do we need to do? We need to draw the Bode diagram. So let's look at what we have here. At the beginning, suppose when you study these problems like this, where k is parametric, it's you want to figure out the k such that just draw the Bode diagrams and the Nyquist plots as k were equal to 1, and then we can do an analysis later. So suppose k is equal to 1 here for now, and well, we have this transfer function. What is the first thing we're going to do? Is we're going to put it in a Bode form. What's the Bode form in this case? Well, you see you've got 2s plus 1. We want it in the form 1 plus tau s. It has to be plus 1 plus tau s, not minus 1, right? So what we're going to do is take a minus out of here, take a minus out of the other term. Two minuses just cancel each other out and they become a plus. And now we have 1 plus tau s, 1 plus tau s. Does it make sense? Yeah, right? Okay, so let's start for the numerator here. We have the term s plus 1. Who's tau? Tau is 1. So 1 over tau is 1, right? And so this is a numerator term. Let's suppose that these are 0 dBs. Then let's suppose that these are minus 20, these are minus 40, these are 20, and these are 40 here. So tau is equal to 1, so 1 over tau is equal to 1, which is this. So this term s plus 1 contributes with a 0 magnitude up to a decade before, and a decade above, it goes up 20 dBs per decade. That's not nice. It goes up with 20 dBs per decade and passing through here. And what happens in the middle? Well, we can just approximate it like this. So please correct me if I'm doing mistakes. This is an s plus 1 term. Correct? Looks good. Tau is positive. It's at the numerator, so it makes sense, right? Should match what we said before. What about the phase? Well. So suppose this is 0 degrees. Let's suppose this is minus 90. This is minus 180. This is 90. This is 180. So what goes on? It goes on that up to, let's mark 1 decade above and beyond the breakout frequency, we have a 0 contribute up to here, then tau is a positive number. The term is at the numerator, so if I'm not mistaken, we get a contribute of 90 degrees. And in the middle, we can just connect them like this, okay? This is the term s plus 1. Okay, now let's go to the next one. I'll switch color to a hope green. So 1 minus 2s, same thing as before. This time tau is equal to minus 2. It means that the breakout frequency is equal to 1/2. So if this is 1, 1/2 is 0.5, so it means 1, 2, 3, 4, 5, it's here. Okay, this term here is 0.5. Okay, so it's roughly here. Okay, so what is this? This is a term that is at the denominator. Okay, so the magnitude has a flipped behavior with respect to what we've seen before. So it's gonna be always a 0 up to this point here, and then it goes down with 20 dBs per decade. So after 1 decade, we should be 1, 2, 3, 4, 5 here. So 20 dBs are 1 and 2. So here now, the cool thing about having this paper, you can actually be relatively precise. So this goes down like this, and in the middle, we can just connect. Okay, so basically we have a different breakout point. What about the phase? Well, the phase, remember always this is 0.5, so this is roughly 0.05, it's 1 decade before, and this is roughly 1 decade above. So 1 decade above, sorry, here. So, well, it's a 0 up to here, then what case are we? It's at the denominator, so we would have a negative, yes? So let's see. 0.5, a decade above would be 5, 0, 1, 2, 3, 4, 5. It should be here, correct? Thank you. Okay, so I just erased that part here. Well, I'll just put it in green. Remember that it's blue instead. Okay, where were we? So this term should contribute minus 90 degrees because it's the denominator, but tau is a negative number, so you have the opposite behavior. Let's go and check it out before, what we wrote before. So where is it? Here. So here we were studying 1 plus tau s at the numerator. And at the numerator, we had this behavior for the magnitude and this behavior for the phase, but tau is inverted. So what we get is 0 up to here, then again pi half here, and this goes up like this. What about the other term? 1 minus 3s. Well, 1 minus 3s is fundamentally very similar. Let me use a different color. 1 over tau is equal to 3. So this is not 1 over tau is equal to 1/3. So this is somewhere here. Now I will not be precise anymore. So same story as before. So the phase grows like this, and the magnitude instead starts here and goes down like this. Okay? How does this help us? Now let's put all these three terms together, and I'll write it in red. So how do we sum them up? Well, up to this point here, the magnitudes, it's nothing happens up to here. Okay, so the red now is the final Bode plot of the whole transfer function. It's 0 up to there. From this point here to the next breakout point here, it starts decreasing with minus 20 dBs per decade, right? Because it's the contribution of the black term. So it goes like this. Then from here to here, it's the green term starts contributing again. So the magnitude goes, you just sum them up, right? This is the nice thing because we're using dBs, so we can just sum up the terms. So it's minus 20 dBs and another minus 20 dBs, that's minus 40 dBs per decade. So up to here, we're gonna go down with twice the slope. And then after this frequency here, there's the blue term that starts kicking in. So this continues going down at 20 dBs per decade. So this red line is an approximation of what the overall magnitude of this frequency response is. Now, what about the phase? Well, the phase is it's a 0, 0, 0. Oh, look, we have three terms, right? Let's look directly at high frequencies, what happens. We have three terms, each one contributes 90 degrees, so it's 90, 90, and 90, it's 270, 270 degrees. And basically means 180. It's up here. It's out of the graph, but the bottom line is that it would grow like up to here. It's a 0, then it starts growing, and it starts growing is faster, then faster again, up to when it gets to 270. Unfortunately, it's invading the other graph. I should have drawn it a little bit more down, but we understood. So how does this help us in drawing the Nyquist plots? So let's look at this for a second. So here we have the space of the imaginary numbers. There's the real axis and there's the imaginary axis. Now, remember that you can, in terms of phases, if you go to this axis here, you have 90 degrees of phase, 180 degrees, 270 degrees, right? And this is 0 or 360 degrees. Well, what do we need to do? We need to draw the polar representation of this same thing with omega being a parameter. So as omega varies, how does the magnitude and phase of this big complex number evolve? Keep in mind that now, when we look at it in the polar plot, the magnitude is basically the distance from 0, and the phase is the phase. No, it's a regular as if it were at every omega. It's an imaginary number. We just plot it where it should be. So let's start from omega equal to 0, no? And let's scan through the omegas and try to track out this graph. So at omega equals to 0, what happens? We have, I'm going to purposely do a mistake now, so I want to see who catches it. I'll just pretend I'll be smooth and then just talk it through, and let's see who catches it. So we have to start, let's look at the limit cases. We have at 0 or very, very, very infinitesimal frequencies, we have a phase equal to 0, so we are starting here. And we have an magnitude equal to 0. So magnitude is the distance. It means our Bode plot starts here. Then as we move over with frequencies, well, what happens? The magnitude stays the same. The phase stays the same as omega increases up to some point where the phases start increasing and going towards 270 degrees eventually at omega equals infinity. So nobody's interrupting me. I already did the mistake. Guys, you're not careful. So, okay, this is the yes. Say it again, sorry? No, K, like now, this is the, I'll get to you. We're pretending we're doing an exercise where you have to find K such that, okay? It's like you're designing a controller. So as I said at the beginning, suppose K is equal to 1 for now, and then we will just keep it in track later. So yes? Exactly that, yes. So 0 dB is not the same thing as 0. 0 dB means 1 in linear. So it's not true that we start here. We start at 1 here, okay? Because the magnitude of the transfer function is 0 dBs, not 0. So as we are here, then as omega increases, what happens is we eventually get to what? So the magnitude stays constant for a while the phase increases. So magnitude constant means we're moving around the origin, so moving the phase but keeping the same distance. So we are going somewhere around here as omega goes. This is omega equal 0, let's say, from plus. And as omega increases, we're moving in this direction. It's really ugly. And what happens? Well, at some point, you see the magnitude starts going down as the phase continues to increase. The magnitude going down, what does it mean? I mean, it's going down a lot down, right? At omega equals infinity, the magnitude is going to be minus infinity dBs, which is a 0, okay? So what we're saying is as omega increases, the phase is going from 0, it passes 90, it passes 180, it gets eventually to 270. This is 90, this is 180, this is 270. So it means that we are wrapping here, and then we're going to cross the others. But as we start getting closer, the magnitude decreases. The magnitude is the distance to the 0. So this basically tells us that we are falling down into the origin. But where do we get to the origin? Do we get to the origin like this? Or maybe do we get to the origin like this? Well, what is the correct solution, right? This has lots of influence on the interpretation of the Nyquist plot later. Well, you can tell by looking at the final phase. That's why I kind of put the accent of let's look directly what happens at omega equals infinity. Because at omega equals infinity, you have 270 degrees. So it means that we are actually approaching the origin from the 270 degrees axis, okay? So fantastic, this is the Nyquist plot. The positive part, then we have to do the symmetric with the negative part. Boom, you have it. See, Bode plots help us do this. Now let's take it a step forward and start seeing how these things actually help us. Well, what do we want to know? We want to know, for example, for what values of k is the system stable, unstable, and so on, right? So as you've seen in the last class, you can use the Nyquist plot to determine asymptotic stability or not of a system by counting the number of counterclockwise encirclements around the -1 point and comparing them with the number of unstable poles of the open loop transfer function. Guys, I understand that this sounds like a little bit crazy, but if you do like repeat it 100 times or maybe do the calculations a few, it will stick. I suggest that you kind of just make sense of it a couple times. Once is enough if you make sense really. And then you just remember the rules on how to draw it. So you don't remember this by heart because you understood it once, but then you don't go and re-question every time how you actually get there. Just remember the method and use it, okay? Because it's really powerful. Nyquist is nasty, but it's powerful. It's going to be the preferred method of analysis going forward, even for more complicated stuff. In future control classes, you'll see more Nyquists than Bode plots and the root locuses. Root loci, whatever. Okay, so what are the Ks that we need to choose? Well, if you think about it here, we didn't really, not knowing what K is, we supposed K was 1. There are different cases that could happen. So let's plot them all out. There's a case in which -1 is here, a case in which -1 is here, a case in which -1 is here, a case in which -1 is here. Depending on how we change K, you can imagine that K is magnifying this Bode plot, okay? So if we have a very, very small K, suppose we're multiplying all of this by K equals 0, 0, nothing, epsilon, okay? Then -1 would be very, very far away from the Bode plot. Let's say that we call this point A here, and this point here B, and this point here 0, okay? So basically we're saying if K is included between 0 and some value Ka, which is the value at which the Bode plot actually crosses the critical point -1, then we would be in this case here. In this case here, what happens? Well, how many encirclements do we have? Counterclockwise encirclements. Well, Shima taught you that you can just take any random line in any random direction. You count the number of the counterclockwise encirclements. I read a 0 here. So we have a 0 counterclockwise encirclements. What about the number of unstable open loop poles? So let's look at this. These are the open loop is this, transfer function. The poles, where are the poles? Where the poles here are 1/3 and 1/2. They both have a positive real part. They're two nasty, unstable open loop poles. So the open right hand, the plane, open loop poles, I don't know, it's a really ugly acronym, we should come up with something better, are 2, right? So these are different, so that means that here we have instability. If you choose K, that is any number from positive number from 0 to some number Ka, which is TBD, then your thing is unstable. What if instead you have K that is bigger than Ka? You can do all the different cases. This is K bigger than Ka. Say it again. Okay, we can talk about it. Then in this case here, you would have K that is smaller than 0 up to some Kb, and here K is much smaller than Kb. And you can do the different cases and see where you get instability and asymptotic stability depending on these different cases. For example, here you would have one counterclockwise, another counterclockwise. So in this case here, 2 counterclockwise encirclements, 2 unstable right-hand plane open loop poles means asymptotic stability, and so on. How you find K and Kb? I'll start with this next time.